In this video, I'm going to solve an example based on the Clipper circuit. So here is the given circuit. Here he's asking about draw the input and output waveforms based on the Clipper circuit. Assume constant voltage drop model. So we know that constant voltage drop model is nothing but each diode has a 0.7 volts drop across each diode. So step one, I'm going to assume, based on the, we have to do the step one, you have to do the current flow directions, I'm sorry. So that's one possible current flow direction. That's another possible current flow direction. That's another possible current flow direction. Remember, this is a AC voltage. AC means it's alternating. Since it's alternating between plus 10 and minus 10, at one point current is going to go in the clockwise direction. At another point current can go in the other direction too. So there is a possibility, if I label the diodes D1, D2, D3, D1 is going to act like a closed all the time. D2, D3, we don't know. Sometimes both of them are acting closed, both of them are acting open, or things like that. Now in next step, what I'm going to do, I'm going to assume D3 closed and D2 open. The reason behind it is, if I assume D3 closed, it's look like a DC circuit, it's easy to solve. That's the only reason I'm assuming D3 closed. And I'll write down the circuit in a second. So here is the circuit after assuming D2 is open and D1, D3 are closed in the sense there is a 0.7 volts drop across them, across those two diodes. Now assuming that's the current passing through those two diodes, I'm using the KVL 10 minus 0.7, so 10 voltage minus 0.7, another minus 0.7, minus of minus 5 divided by 10 kilo. So 10 minus 0.7 minus 0.7 minus of minus 5 divided by 5k plus 5k, 10 kilo. So the current, I end up with 1.36 milliampere. So now I can find the V0. V0 must be the voltage at this point. V0 V0 minus 0.7 minus of minus 5 divided by 5k equal to 1.36 milliampere, equal to 1.36 milliampere. Now based on this, I can find V0. Once you solve for V0, I end up with V0 equal to 2.5 volt. Now I have V0, I need to find the condition. The condition is when this diode is going to, when D3 is going to act like a closed and D2 is going to act like open. So that's the condition we need to find. So for that V0 minus Vn, my apology, my pen is not working properly, so that's the reason the screen is acting weirdly. So here V0 minus Vn, V0 minus Vn must be less than 0.7 volt. Then only that's going to be act like open. D2 is going to act like open. So we know the V0, so V0 minus 0.7 must be less than Vn. So Vn must be less than, so Vn must be less than V0 minus 0.7, which is my apology, Vn must be, now Vn must be greater than, so which is 2.5 minus 0.7 greater than Vn. So as long as Vn, so if Vn is above 1.8 volt, then V0 equal to 2.5 volt. So this is one portion of the solution. So we found that if you look at the waveform, as long as your input value is above 1.8 volt, so 1.8 is going to be somewhere there. So we know what is going on during this cycle, during this period. Okay, so we need to find what is going on during the rest of the cycle. So next one, what I'm going to do, I'm going to assume both D2 and D3 are acting like a closed switch. So in this case, you can clearly see here is my V naught. My V naught is V naught minus Vn must be equal to 0.7 volt based on this. Okay, so V naught must be 0.7 plus Vn. Now I need to find out what are the conditions. To find the conditions, I'm going to take the current passing through this. I'm going to label that as I2, and the current passing through this, I'm going to label that as I1. Now I'm going to say, since both diodes are closed, acting like a closed, I2 must be greater than or equal to 0. Same thing, I1 must be greater than or equal to 0. So let me solve for I2. So I2 is right here going through this 5k ohm resistor. So V naught minus 0.7 minus of minus 5 over 5k must be greater than or equal to 0. So I'm going to substitute V naught value right there, which is 0.7 0.7 plus Vn minus 0.7 plus 5 over 5k must be greater than 0. So if I solve this, 0.7 minus 0.7 get cancelled out. If I move the 5k to the other side, must be multiplied with 0, so 0. So as long as Vn is greater than or equal to negative 5 volt, then V naught must be equal to 0.7 plus Vn. Still I haven't done this part of the problem yet, because now I found one end, I need to find the other end. So if you look at this waveform, now we are saying as long as Vn is above negative 5, so negative 5 might be somewhere here. I know what is going on above, so I need to find what is the upper limit for this. So to find out, what I'm going to do, now I'm going to assume my I1 is greater than 0. There is no way I can find I1 unless I know I total. So I'm going to say, I'm going to apply KCL there at this junction. I'm going to say IT must be equal to I1 plus I2. Sorry, my pen is acting up here. So I2, our goal is finding I1, right? I1 equal to I total minus I2. I'll write down that equation. So this is how I wrote the equation here. I total is 9.3. So 10 minus 0.7. So the voltage at this point is 9.3. 9.3 minus V naught over 5k. So that's what I have. And minus I2. We just had I2 is right here. V naught minus 0.7 minus of minus 5 over 5k. So I2 is right here. V naught minus 0.7 minus of minus 5 over 5k. Based on that, I found I2. So that's the equation. So after solving this equation, I end up with 9.3 minus V naught minus 4.3. So 9.3 minus 4.3, 5 minus 2 V naught must be greater than or equal to 0. So 2.5. So 5 divided by 2, 2.5 must be greater than V naught. So V naught is nothing but Vn plus 0.7. So as long as Vin is less than 1.8 volt, then V out. So based on these two conditions, so this and this, if I combine those two, I'm going to write it down. If negative 5 volts is less than or equal to Vn is less than or equal to 1.8 volt, then V naught equal to 0.7 plus Vn. Okay, now I'm going to come up. So if you look at this waveform right here, it has the whole thing, so we know what is going on during this period. Okay, now we need to find out what is going on below negative 5 volt. So in this case, what I'm doing, I'm assuming the diode D2 is closed and D3 is open. With this assumption, I can say V0 minus Vn must be equal to 0.7. So V0 must be 0.7 plus Vn. Okay, now I have the equation for V0. Now to find the condition, so here since this is open, there is no current passing through it. The voltage at this point is negative 5 volt. Okay, so V0 minus 5 must be less than 0.7 volt. Okay, so based on this, V0 must be less than 0.7 plus or minus 5. Sorry, 0.7 minus 5. So if I substitute V0 equal to 0.7 plus Vn must be less than 0.7 minus 5. So Vn must be less than negative 5 volt. So as long as Vn is less than negative 5 volt, this is my output value. So now I have the values for every whole cycle. This is how my circuit, my waveforms are going to look like. Here is my input values. Sorry, my pen is acting up, so that's the reason you see that line. That's the input. Now my output is going to be, look at this, this is plus 10 volt minus 10 volt. Okay, so if you look at the first condition, what does it say? The first condition, as long as Vn is greater than 1.8 volt, V0 is 2.5 volt. Okay, so 1.8 volt, I'm assuming this is 1.8 volt. So as long as above that pink line, my output is 2.8. Below that, V0 equal to Vn plus 0.7. V0 equal to Vn plus 0.7. So now when the input voltage is 0, what is my output voltage? If the input is 0, my output is 0.7 up to 1.8 volt. So my waveform is going to start at 0.7 and until we reach 1.8. This is 2.8 volt, sorry, I mean that's 1.8. Now it's going to clip at 2.8 volt and then it's going to follow the waveform. Okay, so what is the voltage at this point? It's minus 9.3 volt. So my waveform is going to be something like this. It's going to clip at 2.8. It's going to be between minus 9.3 and 2.8 volts. Thank you.